110 and 111. Question is 6 and think number 1. Alright, so question number 6. What is the amount of heat required to change a given amount of a liquid already at its boiling point to a gas without a change in temperature? Alright, remember that is heat of vaporization. Now it's not heat of evaporization. I know it seems like that would be it, but this is heat of vaporization. So let's make a note for that. Alright, think number 1. What do you expect to cause a worse burn? A gram of 100 degrees Celsius liquid water or a gram of 100 Celsius steam? So which one should cause a worse burn? The 100 degrees liquid water or 100 degrees steam? Which one should cause a worse burn? Just kind of thinking about it and why. Well, hopefully you said it's the steam, because remember the steam is already in that more excited state. So for it to transfer its energy to you, it would have to transmit more energy because it's in that higher state. Plus, it's transmitting more of that latent energy, or that hidden energy as well, whenever it's reaching thermal equilibrium between the steam and your skin. So that's why for that one, it should be the steam. Alright, so for your classwork, because I can't really review with you that well. Well, you can't see me, I just noticed that. Sorry. Alright, so for your classwork, since I can't review with you that much or that well, so the classwork will be, you're going to copy the bold terms and their definitions from just on page 99, just 102. So that's what we talked about yesterday. So kind of help you get started into and start thinking about it. Page 99 through 102. Copy the bold terms and the definitions 3 times, as many as you can in about 5 to 10 minutes. So you shouldn't spend forever on it. 5 to 10 minutes. Try to see how many you can copy and get through. So I would go ahead and pause the video so you can do that. Try to get thinking about it so you can use your class time profitably before we actually start reviewing all together. So again, page 99, just from underneath that heat and changes of state, page 99 to page 102 where we talked about yesterday. So copy those bold terms and definitions 3 times, as many as you can in about 5 to 10 minutes. So then pause the video and then do that. Alright, well hopefully you're back now. So I'm going to ask you the question, so this will hopefully check your memory on not just the bold terms, but also any italicized terms as well. So thinking about solid, liquid, and gas, which one has the most kinetic energy? Most. Gas, perfect. Which one has the least kinetic energy? Solid, that's it. Now of course we're talking about the 3 common states of matter. Alright, if you're going from a solid to a liquid, mainly think of water with this, but this works with any type of solid. Going from a solid to a liquid, what do we call that? Melting. What if it's going from a liquid to, what if it's going backwards from a liquid to a solid? That is freezing. Good job. What do we call that point, that temperature, whenever it goes from, it's bothering me how I'm still on the edges. What do we call that temperature change, temperature point, what do we call that whenever it's going from a liquid to a solid? That's the freezing point. Now if you're going from a solid to a liquid, what do we call that temperature change as well? What do we call that point? Solid to a liquid, melting point. So just making sure that you know all those definitions on page 99. I know it feels a little nitpicky, but you do need to know them. Alright, so thinking about it for, if I need to lower the freezing point of water, I'm just going to write the freezing point of water on the board so we all have a reference point. So 0 degrees Celsius. Alright, so if I'm going from a liquid to a solid, so I'm going to draw a cup so that I won't forget. So if I have a cup, and it has ice cubes on the inside, like my picture. So, and I need my whole cup to freeze. What do I have to do? And it's at 0 degrees Celsius. What do I have to do? Do I have to take heat out or put heat in if I need it to freeze all the way? Take heat out. Good job. What do we call that? Because my cup is 0 degrees Celsius, and as I take heat out, I notice the temperature is not changing, but my cup is becoming more and more frozen. What do we call that type of heat whenever I'm taking heat out, but it's not showing up as a temperature? What do we call that? Latent heat. So remember, latent heat or latent refers to something that is present but not visible. It looks invisible. So just thinking about so that we call that latent heat. If you're talking about specifically, given the mass of a solid into a liquid, we call that specifically, if you're talking about it with 0 degrees Celsius for water. If you're talking about specifically going from a liquid to a solid or a solid to a liquid, what do we call that specifically? It's not just latent heat, it's a type of latent heat. What do we call it specifically? Heat of fusion. So just make a note for that. So heat of fusion. I know again this is a little bit technical, but heat of fusion. Alright, so going back to my question. What if I want my solid cup, what if I want my cup with ice cubes in it? What if I want all my ice cubes to melt? So do I have to put heat into it or take heat out if I want the ice cubes to melt? It's still at 0 degrees Celsius though. Alright, I have to put heat into it. Now what do you call that whenever I'm putting heat into it? Temperature's not changing, but the ice cubes are melting. What do we call that? What is that an example of? Latent heat. And then what do we call that whenever we're changing it from a solid to a liquid? What do we call that specifically? What type of latent heat? Heat of fusion. So your book points out that heat of fusion, that it can go either way. It just depends, are you putting it in or are you taking it out? So the latent heat required to change a given mass of a solid into a liquid without changing its temperature is heat of fusion. We just call it that, but you can go either direction for it. So just make a note, if you're putting it in, you have to add it. And then to take it out, you're going back the opposite direction. So if I'm adding heat into it, it's positive. If I'm taking heat out, it's negative. So your book gives you the heats of fusion for different substances, like for water, we'll use water as a reference point. So water's heats of fusion is 334 joules. So it's the same number for either way. So the latent heat required to change a given mass into a solid, or as your book says, give a mass of solid into a liquid without changing its temperature is heat of fusion, because you're going from a solid to a liquid. That one will be positive. If you're going from a liquid to a solid, it's the same number amount, you're just taking it out. So heat of fusion refers to both. It just depends on if you're putting it in or taking it out. So it is a little bit confusing. Okay, so evaporation and condensation. So we talked about it with we talked about latent heat with changes of state. So this picture yesterday. So make a note that you know, okay, understand, okay, that if they're at the same temperature, it just depends on what direction I'm going. If I take the heat out for the water, it'll freeze. If I put it in, it'll melt. But it's the same reference point. It's that same melting point or freezing point. Typically, freezing point and melting point are the same degree temperature-wise, just depends on what direction that you're going. So typically the melting point and the freezing point are at the same temperature. Again, it just depends on what direction to the door you're going. Same idea. Alright, so thinking back over it from yesterday as well, what do you call the change of a substance from a liquid to a gas? What do we call that? Evaporation or vaporization. Either term works for it. Probably want to know evaporation, but it's heat of vaporization later on, so it's a little bit confusing. There are 5 things or 5 factors that affect evaporation. Now hopefully you should start to learn the 5 of them by this point. Now they technically weren't bolded on page 101, so if you didn't copy them, that's okay. But just make sure that you do know the five factors that affect evaporation. What's one? Alright, hopefully you said temperature is one. What's another one? Surface area of the liquid. What's another one? Strength of air currents. You also have air pressure and properties of the liquid as well. Those are the 5 things that affect the rates of evaporation. So make sure that you note this list as well. So temperature, amount of surface area, strength of air currents, the air pressure, and properties of the liquid. Alright, what do you call a substance that just evaporates quickly? Volatile. Good job. What if it doesn't evaporate quickly? What's the opposite then? Non-volatile. Great for that. Alright, what do we call it at the temperature? Okay, well first off, what do we call it whenever you have evaporation occurring throughout the whole liquid? Like if I take a pot and I put my pot on the stove and I start to have evaporation, not just at the surface at the top, but throughout my whole liquid, what do we call the liquid? We say the liquid is what? Boiling. Good job. And then what's the temperature at which a substance starts to boil or start to have all the liquid at once start to evaporate? What do we call that? What temperature point is that? Boiling point. Good job. Alright. So we talked about this a little bit yesterday. There's a couple of factors we can use to actually control the boiling point. Oops, I skipped freezing point depression. I talked about that yesterday. Alright, so what do we call the point whenever I need to lower the temperature at which water freezes? What do we call that whenever I'm lowering it? Freezing point depression, because I just said it a minute ago by accident. Alright, what do you call the substances that dissolve in a liquid? We're going to talk more about these today. A solute. Perfect. So that one wasn't bolded, but you just make sure that you know it. Alright. So, back on page 102 is kind of where we left off talking about it. that, okay, whenever I have boiling, because this is where you have the water is escaping or turning into its gaseous form. So, whenever I have a pot of boiling water, it's decent pot. Alright, so if I have a substance towards boiling all throughout, it's changing or escaping into its gas form and turning into gas molecules above it. Now, I have the atmosphere that's constantly pushing down. So remember, what's the device that can measure atmospheric pressure? Your exams next week. Barometer. Who discovered air pressure? Not invented. Remember, still didn't invent it. Good job, Torricelli. So just make sure you know. Oh yeah, that reminds me, as a side note. Alright, I didn't count off on this yesterday on the quiz, but remember for quizzes you want to have first and last name of scientist. So if you gave me first and last name, yay, thank you for remembering. But just keep in mind for the future, you want to give first and last name. I did take off this time because I know this is the first one, we've done that in a while. Just make sure you know first and last name for quizzes, you want to note the first and last name of the scientist. So just make a note. Alright, so getting back into this. So whenever you have boiling, all of it is evaporating or boiling all at once. It's not just at the surface. So air pressure is constantly pushing down on the water molecules, trying to keep them locked in. Whenever they have enough kinetic energy, though, they have so much they can overcome that and overcome cohesion as well, and then escape as a gaseous form. Alright, remember, what is cohesion? You know, that's the attraction of the molecules of the same substance. So they have to overcome not only the air pressure, but their own cohesive forces. So that's how come, we talked about this yesterday, that if you increase the pressure on the liquid, that it has to have more energy to overcome it. So your book points out at regular atmospheric pressure, water boils at 100 degrees Celsius. That's the boiling point for water. That's whenever water typically has enough energy to overcome cohesion in the in the atmospheric pressure and have enough to actually boil out and to actually turn into the gas at that point. If I were to go to the Dead Sea, though, remember, I keep pointing to the empty classroom and it makes me sad. Because at the Dead Sea, because it's the lowest point on Earth, remember, that's whenever there's more atmospheric pressure above you. Your book points out water boils there at 94 degrees Celsius. Now again, that's not tons, but that's a lower temperature, and that's whenever, because there's less atmosphere. Excuse me, this is Mount Everest. I'm doing Mount Everest. At the Dead Sea, let me get to the Dead Sea. Let's see. In Denver, Colorado, that's a higher one. Just give me the Dead Sea. I thought I gave me Dead Sea. That is sad. I do not remember. Does it give me the Dead Sea? For sure it did. Well, that is depressing. I'm going to have to go look that up now. So, in theory, we will say that it boils at 102 degrees at the Dead Sea because it has more atmospheric pressure pushing down. Your book points out at Mount Everest that it boils at 71 degrees Celsius because it's so high up. Now keep in mind that this one is just saying theoretically, and I guess the scientists could have put it in a tent to keep it away from the wind and stuff. But because there's less atmospheric pressure, it would boil at 71 degrees Celsius. Alright, we're actually going to watch a quick video about this. Now I know we're filming a light projection screen, so it's going to be a little bit funky, and I can't do anything really about that one because the screen is backlit. It's going to show up in weird lighting on the video. So if you want to go find this video on YouTube, you can watch it there. Be sure to get your parents' permission though before you just start wandering around on YouTube. So make sure you check with them first before you just start looking for it. But I'm going to go ahead and show it because it does do a really good job demonstrating this principle, and I like it. I'm going to show it anyway.
Hey guys, so
I'm going to turn off the lights. I think that'll help a little bit for it, but I'm saying this is the best I can do with this.
we want to try some live experiments, but rather than being in the studio, this time we're actually in Kathmandu in Nepal. As
a side note, you also want to notice his apparel change or the changing of his clothes, because he's at Kathmandu, or the capital of Nepal, which hopefully people remember that as well. You'll notice as they get higher and higher up in the mountain range, now he's not going all the way up to the top of Mount Everest, but because he's going higher and up, it's getting colder and colder, and you'll notice that he starts to get steadily more miserable as the video goes on, because it's getting colder. And you'll notice by the time he gets to the end of it, that he starts having more of a winded sound, because not only is it really cold, there's less atmosphere, so he's getting winded as he's talking about this. So again, I'm sorry, I know it's kind of backlit, and I'm sorry, that's the best I can do for it. You can always find it on YouTube if you want to watch it later, or you could just listen.
Tomorrow, our trekking up to Everest Base Camp. It's going to take us a couple of weeks to get there and to get back down again. So we thought it'd be a great opportunity to have a look at what changes as you go up higher to a high altitude. Will the experiments behave differently? We don't know. So the first one we want to try is this one. We want to have a look at the temperature that water boils at. All right. Okay, now this is a temperature probe. Currently saying we're about 28 degrees. So I'm going to put on our mug of water, stick the temperature probe in, and wait. This may take some time. That is well and truly boiling at a temperature of 97 degrees. Now that is because we are at 1,304 meters in Kathmandu. So at 1,304 meters, water boils at 97 degrees. Well, this seems to be taking forever compared to down in Kathmandu. It's just been sat here for about 10 minutes. We're about 74 degrees. We're starting to get some bubbles. Yeah, this is interesting. Right, I think we got it. So water boils at 3,500 meters at 91 degrees Celsius. So that's 6 degrees less than when we were down in Kathmandu, and 9 degrees less than when we're down in London at sea level. I wonder what's going to happen when we push up even higher, another 2,000 meters to Everest Base Camp. Some friendly yaks, comes with a bit of science. Alright, we got it. That water is definitely boiling at 82 degrees. So back in Kathmandu I think it was 97, then it dropped to 92 when we got up to 3,500 meters, and here at 5,364 meters it's boiling at 82 degrees. Now when you heat up water, you give energy to the water molecules and they turn from a liquid to a gas. They evaporate off, but some of that evaporated gas sits just above the water surface as an evaporated vapour. Now, water actually boils when the pressure of that evaporated vapour matches the atmospheric pressure all around it. So as we've come higher and higher up the mountain, now right up to over 5,000 metres up, there's a lot less air above us, a lot less atmosphere, so the atmospheric pressure is less. That means that to hit that balance point where you get the pressure of the water vapour matching the pressure of the atmospheric pressure, you reach that a lot quicker. And when you reach that point, the gas bubbles can start to form in the liquid and actually boil off. So we only need to reach a much lower pressure of that slight evaporated vapour above that level of water. And that is why water boils at a lower temperature and altitude.
Alright, so that's it for the video. So I'm going to get the lights again and swap back. So again, I'm sorry if it didn't show up super well. It looked like when I was watching it on the screen that it was kind of backlit. Well, that was bad too right now. So that's why I got to turn on the light. But again, you can always watch it on YouTube later if you want to. He did a good job just demonstrating the principle. Okay, so getting back into this, we use this more increasing the pressure to keep it from boiling, just the temperature that cooks it, with a pressure cooker. So that's what your book is showing you with higher pressure increases the boiling temperature, and then it shows you talking about a pressure cooker. A lot of cases, a crock pot is an example of this. I'll go ahead and shift that over so I'll remember to stand over. So a crock pot is kind of like an example of this, or a pressure cooker. Alright, so normally I would have someone read this. I need to remember to stand closer to this side. Normally, I might want someone else to read this, but since it's just me in here, I'll go ahead and I'll read it. Alright, effective pressure in a boiling is used to cook food faster in a special container called a pressure cooker. A pressure cooker is simply a very strong pot with a lid that can be locked shut to form an airtight seal, trapping steam within the pot. As the liquid in the pot is heated, the rate of evaporation rises. The water vapor produced is contained within the pot, raising the pressure above the atmospheric pressure and thus raising the boiling point of the liquid. A weight or spring controlled valve at the top of the pot maintains this operating pressure and thus the operating temperature of the pot. The pressure of a typical pressure cooker is about 103.4 kilopascals above atmospheric pressure, which raises the boiling point of water to 120 degrees Celsius. The high temperature of the pot enables the food to cook much faster than under normal atmospheric pressure. Because remember, it's the temperature of the food that cooks it. So even though the water is not boiling yet, it still has that higher temperature. That's when your mom might use a crock pot or a pressure cooker to cook chili or stew or roast beef because it cooks it faster and it lets those spices blend faster on the inside. Pressure cookers contain an additional safety valve to keep the pressure from the pot from exceeding the strength of the pot. If the pressure were to rise too high, the pot could explode. Your pot only has so much of it, can only withstand so much pressure. You get past that, you have a very real chance of your pot exploding. Also, the lid of the pressure cooker must not be taken off until the water is sufficiently cooled. As with a car radiator, the violent evaporation produced by a sudden drop in pressure can cause a severe burn. So your book kind of talks about this with the radiator of a cat. We don't really see this on the inside of cars too much anymore. So looking at this diagram, you have the vent hood, you have the pressure relating weight, locking cover, sealing ring, and then your actual pot. Now, your book points out as well that if you have the pressure cooker on and you were to suddenly release the pressure all at once, the same thing that happens with your pressure cooker can happen with the radiator of a car. If you remove the radiator cap from the radiator of your car, if it's overheated, all of the water on the inside wants to escape its steam really quick because you had it at a high pressure, and then all of a sudden, once you've opened up that seal, you've allowed that pressure to basically allowed an area of escape for all that pressure, so it wants to go out immediately as quick as possible. That's the reason why on TV shows they'll show them that they take the cap off and like oil or water comes spewing out. That's the reason why. If you take the cap off, all that steam wants to escape immediately. And as well as where you could actually burn yourself really bad. It also typically sprays hot water whenever that happens. So you can get a really bad burn if you do that. So don't mess with the pressure cooker. Don't try to open it until it's properly cooled off on the inside and just let the pressure drop again. Same thing with your car. So your book points out that the engineers use the principle to keep the liquid from boiling with the cooling system of a car. But if you remove it whenever the car is very hot, like if your car radiator is overheated, typically what happens in the TV shows or old movies, don't take the cap off the radiator until it's cooled down. If you take it off right then, because it's so hot, it's basically evaporated on the inside, and so all the gas will try to escape at once. You can get a very bad burn. That's the reason why you want to be careful with this. Alright, so your book starts talking about boiling point and altitude. So again, if you go higher up in the atmosphere, there's less pressure. So your water will start to boil, or any type of liquid will boil at a lower temperature if it has a tendency to evaporate. Alright, so Dead Sea, let's see. So it says in this one, in New York City, that regular atmospheric pressure, 100 degrees Celsius. Dead Sea, it does tell me. I thought it told me somewhere in here. Alright, so Dead Sea, 100 degrees Celsius. I thought I remembered seeing it, I just couldn't remember where at. So at the Dead Sea, so again, not super high, but there is more pressure. So it boils at 101 degrees Celsius, New York City degrees, 100 degrees Celsius. And then you get higher up in the atmosphere, 71 degrees at the top of Mount Everest. Alright, so she's pointing out that, okay, if you have a higher pressure, you're going to boil at a higher temperature. Alright, so moving on from that. Alright, we call it to where the addition of solutes to change the boiling point. We call this boiling point elevation. Remember, we already talked about solutes. What's a solute? A solute is a substance that dissolves in a liquid. So whenever we're talking about it, we're talking about with salt and water. I'm going to get really good at drawing these glasses after doing this for a couple of days. So I have my cup of water, and then I throw in salt on the inside of it. Now remember, a solute keeps keeps the liquid from forming into that solid because it clutters it up so that the water molecules have a hard time walking around it to form up the ice. So remember, since the molecules can't freeze very well, It's called a freezing point depression because it lowers the freezing point. You have to take out more energy for your water to actually freeze in the ice. So it's the same idea though. If I want to raise the boiling point, I need to increase the temperature of the water. I can still throw in a solute, and it'll still get in the way. So since the water wants to evaporate, it has to go around the solute or the salt mixed in with it. And so because of that, it'll raise the boiling point because the water has to have enough energy to get around the solute mixed in with it. So since it's going around it, it can't evaporate as well. So you have to give it more energy for it to actually evaporate it out. So we call that boiling point elevation. So freezing point depression, so going down. Boiling point elevation is going up. So you're decreasing the freezing point and you're raising the boiling point. You might do this if you want to cook maybe eggs or pasta. You might have noticed your mom takes a little bit of salt and throws it into the liquid. Sometimes it's to add flavor to the noodles, like for if you're cooking noodles, typically add a little bit of salt to give it flavor. But it also increases the temperature. It also increases the boiling point. So whenever you're trying to boil noodles, it'll boil them a little bit faster. I do it with eggs, not because I'm trying to give my eggs the flavor because of the calcium, but if I'm trying to boil a pot of eggs to make a hard-boiled egg for salads or for egg salad, something like that later on where I need, or deviled eggs. If I need to boil eggs, I will throw salt in the water. Not because I want to add salt to my eggs to make the eggs taste salty. The shell is still on the outside, so it can't really get in that well. But I'm raising the boiling point of the water so that way it'll cook it just a little bit faster. So that's the reason why sometimes people will do that. Alright, heat of vaporization. This is the same idea of heat of fusion, to where you're going from a liquid to a solid or a solid to a liquid. It's the same term basically, just depends on what direction you're going. So latent heat required to change a given mass into a solid, from a solid into a liquid, we call it the heat of fusion. And it just depends on what direction you're going. Technically, it refers to turning the solid into a liquid. But it's the same idea either way. If you're putting it into it, you're melting it. Take it out, it's the same amount, you're freezing it. So this is the same idea, heat of vaporization. So whenever you have water evaporate, it turns into the gaseous form of water or water vapor. Technically, you're not supposed to be able to see it. Whenever you see your breath form on a cold day, it's because it's losing or condensing back in the atmosphere, but your book's just pointing it out. That is changing into water vapor. Let's see, I feel like I lost my spot for a second. No, I don't think I did. Alright, so whenever you're talking about it on this page, on page 103 with 104, you're getting into heat of vaporization, having it change into that gaseous form for it. So this is heat of vaporization. It sounds like it should be heat of evaporation. Technically it's heat of vaporization. Make a note of that and mark that. Your book has this diagram. We'll come back to this diagram as well. But if you're talking about this where you have 1 gram of water at 0 degrees Celsius, you have to put in a lot more energy for it to turn into steam. I know it looks basically white on this picture. So if you look in your book, you'll notice it's a slightly different color, but I know it looks completely white. But it's basically that it's turned into steam at this point. You'll notice this number is a lot higher than the heat of fusion going from a solid to a liquid or a liquid to a solid. That's because this has to overcome atmospheric pressure as well as cohesive forces. That's why this one is so much more energy. So I have to put in 2,260 joules for it to evaporate or turn to steam. If I need it to condense or go back into water form, I have to take out 2,260 joules of energy back out from it. So it's kind of like the same idea with the heat of fusion, depending what direction you're going. It's the same terminology, it's just depending on if you're putting heat in or taking heat out. So putting heat in, I have to put heat into it if it's going from a liquid to a gas. I have to take the heat out if it's going from a gas to a liquid. So make a note of this. Now keep in mind, what do we call this type of heat where it's there but it's not having a change in temperature? You'll notice for water, it's still at 100 degrees Celsius either way, but I'm changing the state. What do we call it? To where I'm putting energy in this case a lot of energy, a whole lot of energy, or I'm taking a lot of energy out, but it's not showing up as a temperature change. What do we call that? Good job, latent heat. So this is another example of latent heat. Heat of fusion was earlier if we're talking about between a gas and a solid. So this is heat of vaporization if you're talking about a gas and a liquid. So it just depends on what direction that you're going. So putting it in, it's positive. Taking it out, it's negative. Alright. Let's see. You'll notice that the heat of vaporization is much greater than the heat of fusion. So it is much larger. So your book gives you this chart. You're going to need this for a little bit for homework and a little bit later on. But your book's just going ahead and just giving it to you. Alright, evaporative cooling, looking on page 104. So this is why whenever your body's hot, it starts to sweat, because that's how you were designed to cool down your body. Now it feels gross and nasty, but that's the reasons for it. Let's read through this one. And again, normally I'll call someone else to read it, but I'm alone, so it's okay. Because evaporating molecules carry thermal energy with them as latent heat when they leave, evaporation results in a dissipation of heat. God is the human body to use this principle to cool itself. When your body gets overheat from exercise or environmental conditions, your brain automatically signals your skin to release liquid water to the surface of sweat. This water evaporates, carrying thermal energy with it, and your skin cools off. Without the ability to sweat, your body would quickly overheat in warm weather it would overheat in warm weather or during exercise. Unlike humans, some animals such as dogs lack the ability to sweat. Dogs use evaporative cooling for God equipped them with large tongues and other evaporative services within their mouths. When a dog begins to overheat, it opens its mouth and begins to pant. The air currents passing over the warm, moist membranes in its mouth cause rapid evaporation and effective cooling. God's provident design is evident everywhere in His creation. Alright, so what this means is that this is talking about how you're having evaporative services on your body, like with your glands and with your skin. This is whenever you start to sweat. So that way, as you have your sweat evaporate, it'll take some of that heat with it. Now down here in Georgia, because we have so much humidity in the air, it has a hard time evaporating off our skin. And if you go down deep south as well, it also has a hard time evaporating that moisture off your skin. If you were to go to a drier area like Arizona, where it's not as much moisture in the air, that's whenever you sweat. As you have the sweat evaporate off your skin, it takes that heat with it and it cools you down. But again, because you live in a humid area, you have a hard time with it. Your book also points out that dogs also work on the same principle. Even though dogs don't sweat, you don't see a sweaty dog. That's why they stick their tongue out. So that way they have a large evaporative service. So that way the tongue will have the air currents blow on it with the panting or with the wind. That's why it helps pull the heat off their skin and off their body, so it helps cool down their body. So again, just different designs for different living things. Alright, let's see. I think I've covered everything that we need to get started with the practice. Alright, let's talk about condensation really quick. So condensation is going backwards. So I decided, I've kind of already talked about this. So condensing or going back from a gas to a liquid. Make a note of that. That is condensation. So your book points out heat of vaporization involves both evaporation and condensation. So it's the same term and it's the same amount of same amount of energy. It just depends on if you're adding it in or if you're taking it out. Kind of like we talked about yesterday with heat of fusion. Depends on what direction through the door that you're going. Same idea. Are you adding it in or are you taking it out? But this is known as a type of latent heat because it's not showing up as a temperature change. Okay, I think that's everything now. So let's get practice with some of this class where I can start getting you practice with this. Alright, so look on page 105. You've already done number 1, but number 2, 3, and 4. Alright, so try to do number 2 by yourself. You'll notice this one is about acetone, not water. So your book puts out again, you're going to have to use page 100 and page 104 to answer the following questions. So read through that one for number 2 and then pause the video and then try to solve it on your own. I'm going to go ahead and erase this so that way I can help get you started for the next part. If you're super brave and you want to try number 3 by yourself, okay, good job. But I'm going to walk you through, at least get you started for that one, because that one's a little bit trickier. So go ahead and pause the video while I finish swapping this out, and so that way you can get started on it. So if you're watching at this point, then that means hopefully you've already paused it and already tried to solve it. Alright, so this is heat of vaporization. So for this one, it's saying how much heat does 4 grams of acetone at 56 degrees Celsius release whenever it condenses. So if it's going from a, excuse me, it is going from a gas to a liquid. And so because of that, it is losing heat. So we'll add the negative sign later on for it. But it's asking, okay, how much heat is it losing? So this one is losing heat. So it has to have or lose 513 joules for every gram that it has to give off whenever it is condensing from a gas into its water form. Now your book points out this isn't just 1 gram though, this is 4 grams. So hopefully you noticed, okay, so kind of like in the homework yesterday, I should multiply 4 times this and I'll give you my answer. So yeah, that's it. So 2,152 is what you should have gotten in your calculator. Now this is how many, now first of all, is it multiplication or division? Multiplication. So how many sig figs? 2. How many sig figs? 3. In multiplication and division, do you go off the number or do you go off the place? You go off the number. So this answer should have 2. So if I went around this with 2 sig figs, what do? Good job. So that would be the final answer. So 2,100. Remember, no decimal point. So that way these last 2 zeros don't count. So that's the answer, problem number 2. Problem number 3, I'll talk you through it, kind of gets you started, but this one's a little bit harder. And this one is a good review because it goes back to specific heat as well. How much heat must be added to 5 grams of solid lead at 30 degrees Celsius to convert it to a liquid lead at the melting point? And then it tells you, hint, the specific heat of lead is 0.13 joules per gram times degrees Celsius. Alright, so if you look back over, you'll notice, okay, if I'm going for, I need to see, okay, first off I have a temperature change for it. So how much heat must be added to 5 grams, yeah, it's 5 grams of solid lead at 30 degrees Celsius to convert it to a liquid lead at its melting point. So if you look up at the melting point, you will notice that the melting point for lead is not 30 degrees Celsius. So look over on page 100, that should give you the melting point for it. So you find lead, you look over, it's about the middle column of it. So you look over, melting point of lead. Oh, that's not 30 degrees Celsius, that's 328. So for this substance, I'm going to go ahead and write this so I won't forget. Alright, so it's saying how much heat must be added at 30 degrees Celsius. I'm going from 30 degrees Celsius to 328 degrees Celsius. It's asking me total how much heat must be added to convert it to liquid lead at the melting point. So I'm going from 30 degrees to 328 degrees Celsius. As a side note, 30 degrees Celsius is about room temperature. This is how come lead is like solid at room temperature. You have to heat it up a lot for it to actually show and actually for it to start to melt at that point. So, what would be the equation we would need if we're working with a heat change? You have mass and you have specific heat. I know this has been a while since we talked about this. What equation should you use for this? Hopefully you said, okay, it has to be the equation with specific heat. So remember, the equation if you're finding the specific heat is this, but we can shift it around to find heat if we need to. So it becomes Cm delta T equals Q, so just shift it over. And this is the equation we're going to need since it's asking for how much heat has to be added. Remember, Q is heat, so we're trying to find Q at this instance, and then we'll have to melt it as well. So right now, we should figure out how much heat is needed just to raise the temperature up to that point. Alright, so it tells me I have to know the change in temperature. So if I'm going from 30 degrees to 328 degrees Celsius, what's that difference? What's that change? Good job, 298 degrees Celsius. Alright, what's the mass of iron? It tells you that at the top of the problem. So 5 grams. Alright, what specific heat of iron? It goes ahead and it tells you this one. At 0.13. I'm going to leave off the units for it just to keep it neater for right now. Alright, so I have to multiply these 3 things together to find out just the heat to raise the temperature. Now, we're not even melting iron yet, so don't think you're done. So multiply these 3 together, and that'll tell you at least what's the first part that you need. You can pause the video if you need to, but I'm going to keep going for it. So for this first temperature change, the first amount is I'm going to get 193.7 joules just to raise just the temperature. So down here, 193.7 joules, and then I wrote it up here so I won't forget because I'm going to need this later on. So keep in mind, we're going to round sig figs at the very end, so I'm not going to worry about it right now. So 193 is about to layer at this spot. I'm trying to make sure. 93.7 joules. That's just to raise the temperature. It's asking though, not just to raise the temperature, to convert it to liquid lead. It's also asking about the melting point. To say, okay, I don't want to just raise it to that temperature, I want to melt it as well. Alright, so remember, I have to look to see, okay, what is the heat of fusion then for lead since I'm going from a solid to a liquid. So if you look on page, I believe it's still on page 100. I should have not moved my post-it note. So notice, okay, what is the heat of fusion for lead? You'll notice for this one that it is 24.6 joules per gram. Now I don't have 1 gram of lead. How many grams of lead do I have? 5. Good job. So it's 5 grams times this. That'll tell me how much energy I have to put in it to actually melt my lead at this point. For this one, it's 123 joules. Now, you're still not done once you found them because it's asking me what's the total heat required. So I have to take this amount and add it to this amount. And that'll tell me what my total amount of heat is needed in order to raise the temperature and then to melt my lead as well. So, go ahead and add those up. As you can tell, you get 316.7 joules. Now we can go back and look at sig figs properly. Okay, so for this one, your book points out you started with 5 grams of a substance, and then it says 30 degrees Celsius specifically with a melting point, and then oops, not 30 degrees Celsius. Excuse me, I'm looking at the wrong column. Nope, I was looking at the right one. 30 degrees Celsius with a decimal point, and also I have 5.0 grams. Okay, did it give me anything else? 0.13. Alright, so since I worked with multiplication all throughout this, and then the last little bit was addition, so this one is a good review section for it. So, looking at all of this, where does this, looking at, because our last step was multiplication, we want to go rounding based off that, but we did use multiplication all the way up to this point. So, looking at this substance ends in the tenth, this one ends in the hundredth, this one ends in the ones, and this one ends in the hundredths. I'm drawing a blank, sorry. So, that's probably the reason as to how come for the last significant figures you want to see, okay, since that was our last rule, we want to round based on that as well for it. Keep in mind if you're going off just multiplication, you would want to go off the number of sig figs, and that would be 2 sig figs. So rounding this to the same place though, this would be 317 joules. So as the answer for this one. So again, if you were to round throughout the whole thing with multiplication, you would end up with 2 sig figs, but that's why you want to wait until the very end to make sure that you end up with proper sig figs for it. Let's see. Alright. So, if you have any questions about how to solve, be sure to email me so I can help you out with it as much as possible. I don't think I have enough time to start the next one. If you want to try problem 4 as best as you can, this one though, as a hint, has 5 steps because you are going through the 3 temperature changes of the 3 different states of water, as well as using the boiling point and the freezing point. You're using heat of vaporization and the heat of fusion as well. So because of this, that's probably the reason why I'll go ahead and wait and we'll finish that one tomorrow, because I want to make sure I give you enough time with the classwork as well. I don't think I have enough time to fit this whole thing in. Alright, so I'll go ahead and we'll stop there. Your homework for tonight is to read pages. Let me get over there. Let's see. Read pages, there it is, 105 to 107, 105 to 107, answer on page 110, question 7, And on page 111, the chapter 5 review, identify 8. So answer on page 110, the question 7, and on page 111, the chapter 5 review, identify number 8. Don't forget the second draft of your background is due tomorrow. Email your parents over what we're going to do about that. But you need to be able to look at your second draft. That way, as I'm talking about what it should look like, you can have a copy in front of you. So maybe it's just on your computer screen, or maybe your parents have already printed it out for you. Either one is fine. You need to at least have it with you in some way, so that you can check to see, okay, does it match with what the book is? You're also going to need your STEM project book tomorrow, as well as your regular textbook. Alright, I'll go ahead and let you go. Have a great